Hello everyone, welcome to this course again. As usual, let's review what we have talked about in lecture 7. So in the last lecture, I have covered what is hyperparameter and how we can tune the hyperparameter. I give you this workflow uh, on how to tune the hyperparameter. We can split the data to the tuning data, testing data, and validation data. We will tune the model with different hyperparameters in the tuning data first, and we will also evaluate those models in the validation dataset. And then we will select the hyperparameter whose errors on these two datasets are smallest. And then finally, we will evaluate the final model in the testing dataset. This is our normal workflow to tune the hyperparameter. But in the method that is covered in the last lecture, there are sometimes problems exist. For example, you can see that if we use this workflow to tune the hyperparameter, we need to split the data, right? So here we need to split the data to the training data set and the validation data set. And so this result would be dependent on your split. And different people will have different split on the data. So actually, we don't want your result are very dependent on the split. And another problem with this method is that we will require a validation dataset. What if sometimes we don't have this validation dataset? If your data set is very small and you don't have enough dataset to create this validation data. So sometimes we don't have this validation data. So how can we tune the hyperparameter under this situation? Therefore, in this lecture, I will cover also a very important concept in machine learning, which is typically used for hyperparameter tuning. That is called cross-validation. Okay, sometimes CV for short. Okay, don't confuse this CV with computer vision here. It's just cross validation. So this is sometimes typically used for hyperparameter tuning. Okay, of course, this one can use for other purpose, but it mostly works for hyperparameter tuning here. Okay, there will be two methods that I will cover today. The first one is the name is KFolder CV. So this will be KFolder cross validation here. As usual, I will start with an example here. For example, so here k is a variable. You can choose k as some positive integers here. If I choose k equals 5, it will be 5 folder CV. And if I choose 5, it means I will split the data into 5 parts, uniformly distributed 5 parts. Okay, suppose we have the data like this. Okay, and suppose this is our data. And 5 means that I will split this data into 5 parts uniformly. 1, 2, 3, 4. Okay, suppose these 5 parts are uniform. And firstly, we will use the first part as the testing set or the testing data set. So this shadow area is for test, and this area without shadow is for training models. It's for training, and this part is for testing. Okay, and we said that we use this CV for hyperparameter tuning. If you remember in our ridge regression, what is our hyperparameter? In ridge regression, our hyperparameter is the regularization coefficient, that is eta. We need to tune this eta, means that we need to find eta that has the smallest error. So we will choose different value of eta. Suppose here we firstly choose the eta as 0.5. Okay, and we have all the data, and we use 5-folder cross-validation. And let me adjust. Okay, and if we have this one, if we have done this, it will give us a model, right? So this training in this data set will train a model, and we will test the model on the testing data here. So here in this one, we will have some error, and this error we can split this error to the tuning error and testing error. We will say them differently. Suppose in this one we have the tuning error, that is say tune-1, and of course we will have some testing error also. This is 1. So this 1 means that this is the testing dataset is the first folder here, and then we will move this shadow to the second part. Let me copy this one. This is the data we have, and also these 5 parts, and then we will use this second part as the testing, and we will use the others as the tuning. So you can see that if I move the shadow from here to here, our data for tuning the model is different, right? So we will use this part to train the model. So we will have a different model. If we have a different model, the error would be also different here, and the error would be -2. We have the tuning error, and we have the testing error here. Of course, you need to repeat this process 5 times. And let me copy. And the last one would be you use the last folder as the testing dataset, and you use all the others to train the model. Okay, and of course you will also have some error here, but you will give them a different index because they are different values. Okay, and it's very clear that you will have 5 errors because this is you have split the data 5 times, and you should also pay attention that all these folders are under the hyperparameter of this value. So here, although we have 5 arrows here, we will take the average of these arrows. We will take an average, and this arrow would belong to the arrow of when we take the hyperparameter as 0.5. And here is what you will do. So for each eta, this is eta because we are talking about a ridge regression. For example, For other models, you will have other hyperparameter. So for each hyperparameter, you need to calculate the average error. And maybe I will denote this as error, average. And this average error will have the tuning error and testing error. And you will take the average of them. And it's just the equation to calculate the average, and you sum from 1 to 5 of your tuning error and divide it by 5 to calculate the average. Also for the testing error, and you sum these values together, and you divide it by your k value here. So here k equals 5. You can choose other values such as 8 or 10. It just requires more time to compute for your computer. And this error is for one hyperparameter value. And if you change the value, for example, to 2, you will repeat this process again and get another average error here. Okay, and here is what you need to do next. And this is based on eta equals to 0.5 here, and then you should change the hyperparameter, because this is for tuning. Because this is for tuning the hyperparameter, so you need to try as many hyperparameters as possible. So you need to change the hyperparameter. You usually will give it a range and change the hyperparameter, for example, eta, and repeat this calculation. You change a value of eta and you repeat this calculation. And of course, for each model, you will have different error. For this error, you will also need to calculate the average error here and record the average error. This is important because the average error is the evaluation. We need this evaluation to evaluate if this hyperparameter is good or bad for train the model. And you need to record this average error here. And lastly, and you have a set of hyperparameter and you have a set of corresponding average error. So now it would be easy for you to decide which hyperparameter is good for tuning the model. You just pick the hyperparameter whose average error is the smallest, right? So this makes sense. And lastly, and you just decide or choose the optimal hyperparameter. For example, eta in ridge regression, you just decide the hyperparameter by choosing the smallest error. And I can give you a diagram to help you better understand this. Also, for example, if let's suppose we still use the example of ridge regression. So ridge regression, the hyperparameter is the eta, is the regularization coefficient. And here the y-axis would be the arrow. In linear regression problem, the arrow would usually be MSE. So the MSE would be the mean square arrow here. And as you change the value of eta, this average value would also change. Suppose you get a curve like this. Okay, maybe this is not that accurate, but you can see, although we have the training arrow and testing arrow, I just draw one curve here. You can, of course, draw them separately, maybe something like this. It's just for demonstration. Maybe not, it's not accurate. Maybe this is testing. This is maybe testing, average testing arrow, and this would be the average tuning arrow here. So as you increase the eta, these tuning arrow and testing average arrow would give you a diagram like this. So in this diagram, you will be very easy to find the optimal eta. It would be maybe a value here. So this is the best hyperparameter. And so this means that you have found the optimal hyperparameter. So this process is called the hyperparameter tuning by using this KFolder CV here. Because you can, if you use larger K, you will tune more models here, right? If you use 20, so this shadow block need to be moved 20 times. So here the arrow, you will have 20 arrows here, and it requires more time to compute. Okay, and here I have a picture like this, and okay, and in real practice, we may put our data like this, and again, this is all of our data. And a step we will still have is that we will still split the data into training data and testing data, because remember that we will never train any data on testing data. So here in this example, although I use all of our data, but in practice, we'd better do like this. We will still split the data into two parts, training data and testing data here. And then we will do this KFolder CV in this training data set. For example, we just said we choose eta equals 0.5. If we choose 0.5, we choose 5 folder CV, and we will run the model, run the training 5 times like this. Each folder will be act as the testing data, and all other folders will be the training data. And here we train a model, and here we train another model, and we have 5 arrows, and we take the average of these arrows, and we will have one arrow 1, and then we change the eta to maybe to 2, and we will have arrow 2. And we can also choose other eta, and we run this algorithm, ridge regression algorithm 5 times to get another arrow. And then we again will get some curve like this. Once we decided the optimal hyperparameter eta, we will then eventually test our model in a testing data set. And this is for final evaluation. So Here, one more step is that we will still do this split. Okay, so this is for KFolder cross-validation. I hope you have understood this. And the second method I will talk about is just a unique scenario of KFolder CV here. So the name of it is LeaveOneOut CV cross-validation, sometimes LOOCV for short. And leave one out means we will just leave one sample for testing. So here in KFolder, we will have a set of samples for testing. But in this one, we will just have one sample for testing. So this part, LOOCV is a unique situation when K equals n here. If you remember, the n is just the number of samples. It means that if we make our folder equals to the number of our samples, it will change the KFolder CV to LOOCV. And let me write the definition here. This means we only take one sample as testing data, and all others are tuning data. And this is not finished. We need to repeat this by n times. And here n again is the number of samples or number of data. Here n is the number of samples. Because we have n samples, we need to repeat this for n times. Here we just repeat this for k times. Okay. If you don't understand, no worries. Let me draw a diagram again for you. Okay, suppose this is our tuning data here. We said we just take one sample for testing, and suppose this is one sample we have, and this one sample is for testing. And all the others are for tuning. Okay, and then we will repeat this n times. And copy. And maybe the last one would be this final data is for testing, and this one is for tuning. And this one is for testing. Okay. And the process would just be the same as the KFolder CV. Again, for each value of hyperparameter, for each zeta for hyperparameter, okay, for each one of them, we need to repeat this. And you remember for each of these, we train a model and we calculate the error. We train a model, we calculate the error. And then what we will do is we just need the average error for each hyperparameter. And we need to calculate the average error. So here I will just copy this equation. And so this time it's not just 5. Since we repeat this n times, so the average value arrow would be divided by n. And the summation is also, we have n separate arrows, and we need the average of them. So this arrow is belong to each hyperparameter value, and is what we want. Okay. So these contents are all I want to cover. So here I want to make each video shorter. Thus, you won't feel bored to watch very long videos here. So in this one, we have talked about the cross-validation, and it is usually used for hyperparameter tuning. We talked about 2 methods. One is the KFolder CV. Another is a typical case of KFolder CV. It is LeaveOneOut CV, LOOCV. And the difference between them is that, of course, this one, KFolder one, will be ran faster. And this one, LOOCV, would require longer computing time. Thus, if you have more data or your model is very complicated, if you use this one, you will need longer time to run this algorithm, because it will repeat n times for each of your hyperparameter. And this one, it just repeat k times, and k is 5 or 10. And if you have 1000 sample, this n is equal to 1000. For each hyperparameter, you need to repeat this 1000 times. So this is very expensive. But sometimes this one, LOOCV, is more robust. I think that's all the contents I want to cover today. I hope you have learned what is cross-validation. I will stop here. Thank you.